Have you ever just looked at the world around you and wondered, how does all of this work? Well, that's what physics is all about. But don't worry, this isn't going to be a dry physics lesson. This is an explainer on a really powerful way of thinking, a method you can use to look at any complex problem and find a little bit of clarity. So let's dive in.
For a lot of us, the word physics just brings up these images of blackboards covered in impossible equations and super abstract concepts. Kind of feels like a subject that's just for a handful of geniuses, right? We see it as this huge, intimidating mountain of math. But what if that's just completely the wrong way to look at it?
And that's really the big secret here. The power of physics isn't about having some special kind of brain. It's about having a specific process. It's a repeatable, learnable method for asking questions, for simplifying all the complexity out there, and for building knowledge from the ground up.
So here's our game plan. We're going to walk through this exact method. First, we'll reframe what physics even is. Then we'll get into the core tools, like simplification and experimentation. After that, we'll build up to a solid 4-step strategy for solving problems. And then, at the end, we'll see how you can apply this way of thinking to, well, pretty much anything.
Okay, first things first. We have to completely change how we think about the subject itself. Physics is not some static library of facts and formulas that you just have to memorize. It's an active, dynamic process of investigation.
So the common view is that you memorize a formula, you plug in some numbers, and you chug out an answer. But a physicist, they see it completely differently. For them, it's all about inquiry, about deeply understanding a concept before you even think about the math. The laws of physics aren't these fixed rules from on high. They're relationships we've discovered and tested through experiments. It's a huge shift from just finding the right answer to actively testing ideas. And this whole approach is built on a few key principles. It all starts with experiments. That's where real knowledge comes from. It's about getting an intuitive feel for an idea before you give it a fancy name. It's about using precise language, because in science, words really matter. And maybe most importantly, it's about building a bridge between words and math, making sure those equations actually mean something to you, instead of just being a puzzle you have to solve. So if physics is a process of asking questions about our incredibly complex world, where do you even start? Well, one of the most powerful tools a physicist has is simplification. To understand any part of the world, you first have to decide what you're going to ignore. And this whole process is called modeling. A model isn't the real thing. It's a simplified version made on purpose. And the key word there is decides. The scientist is in control. They're actively choosing which details are essential for the problem they're trying to solve and which details are just noise that they can safely ignore to get to the heart of the matter. Okay, let's take a seemingly simple action, like walking. If you really think about it and try to analyze everything at once, the movement of every single joint, the swing of your arms, how your torso keeps you balanced, it's just overwhelming. You wouldn't even know where to begin. So what does a physicist do? They simplify. They might start by ignoring all of those tiny details and modeling the entire person as a single dot, just a point, moving from one place to another. And suddenly, that's a problem you can actually start to analyze. How fast is that dot moving? Is it speeding up or slowing down? And this is a core concept, the point-like object. It's often the very first step in modeling. We can treat a whole car as a single point on a map, or an entire planet as just one point orbiting the sun. We haven't lost the essence of the problem. We've just cleared away all the distracting details so we can actually focus. Okay, so if modeling helps us simplify problems, how do we use those simplified models to actually build new knowledge? Well, that comes from a structured, cyclical process of discovery. It's the very heart of the scientific method. Think of it like a loop that just keeps going. You start with a hypothesis, a testable idea. Then you design an experiment specifically to check it. Now, this next part is crucial. You make a specific prediction. You say, if my hypothesis is true, then this specific thing should happen. Finally, you run the experiment and see what you get. Does it match your prediction? If it does, great. Your confidence in the idea grows. If not, it's back to the drawing board to tweak that hypothesis. This is literally how science inches forward. And what's really interesting about this toolkit is just how precise you have to be. Take this tip about forces. In physics, forces are what we call vectors, which is just a fancy word for something that has both a size and a direction. So you can't just add them up like numbers on a grocery list. Their direction matters. In fact, two really big forces can completely cancel each other out if they just point in opposite directions. This kind of precision in language and in the rules is absolutely essential. All right, let's get to the most practical part of all of this. How do you take all these big ideas and use them to solve an actual real-world problem? Well, it turns out there's a blueprint, a reliable 4-step strategy that you can use for almost any challenge.
Here it is, just 4 steps. First, you sketch and translate the problem from plain English into a picture with clear physical stuff. Second, you simplify and diagram it using a model and some kind of visual. Third, you represent it mathematically. That's turning your picture into equations. And fourth, you solve and, this is the most important part, you evaluate your answer to see if it makes any sense.
So let's try this with a real example, calculating the force on a crash test dummy. In step 1, you don't do any math at all. You just draw a quick sketch of the car and the dummy. Then you start translating the words. You could circle the things you know, like the dummy's mass and its speed, and maybe put a box around what you're trying to find. In this case, the force.
Now for step 2, simplify and diagram. We're going to model that whole complex 60-kilogram dummy as just a simple point. Then we draw what's called a force diagram, a super simple but incredibly powerful tool that just shows all the forces acting on that point. And here, the main one is the big push from the airbag, slowing it down. Step 3 is where we build that bridge to the math. We look at that force diagram we just drew and we translate it into an equation. And the perfect tool for the job here is Newton's second law. The sum of the forces equals mass times acceleration, or F equals ma. Our diagram tells us what the forces are, and this one beautiful simple equation connects them all to motion. And finally, step 4, solve and evaluate. We plug in the numbers, do the calculation, and we get a force of about 1,900 pounds. But we are not done. This is the crucial last check. We have to ask ourselves, is this answer reasonable? I mean, 1,900 pounds sounds like a lot, but for a high-speed car crash, the sources confirm that, yeah, this is a realistic and actually very survivable amount of force. That final check is what separates a student from a true problem solver. Look, this 4-step strategy isn't just for physics homework. This entire mindset of simplifying, of modeling, of testing, and of evaluating is such a powerful tool for thinking about any complex system you might encounter. When you learn to think like a physicist, you're not just learning about forces and atoms. You're really acquiring a process for how knowledge is built in the first place. You're learning how to look at a claim somebody makes and ask, okay, but what's the evidence? These scientific reasoning skills are like a superpower you can transfer to your job, your finances, and how you make big decisions every single day.
We've just walked through a blueprint for solving a physics problem. But really, think of it as a blueprint for finding clarity. How could you use these same 4 steps, sketch, simplify, represent, and evaluate, to break down a complex project at work, or to plan out a personal budget, or even to figure out how to tackle a difficult conversation? The world is full of complicated problems. Now you have a new way to think about them. So, what will you solve first?